past like 3 months. So it's a fun setup that way. Okay, cool. So I'll wait a little longer, but I'll get started with the attendance quiz and pre-lab Zoom feedback as usual. So we have like a similar program to usual. I'm not going to go through every bullet point. We also have our attendance quiz, and as usual, oh no, I forgot to clone this. 1 second. I'm going to stop sharing my screen, but I'll send this in the chat while I fix this, because I have occasional access issues with my PowerPoint for some reason. So let me fix this. Yeah, the code is 3222 for Canvas. And let me start this up again. Okay, cool. Great. Okay, we're back. Yeah, and this week we're asking you guys about whether you've used the we've used the Friday student office hours or not. This semester we've had like some varying usage of those office hours, and if they were useful to you, if you did go to them. And then we also have our pre-lab Zoom feedback, which I'll open up now, so you guys can let me know how well you understood this week's lecture. Because this is a second round of math for quantum. So if we covered a lot of the topics in kind of less explicit phrasing throughout the semester. Like a lot of things that were covered explicitly this week were covered technically when we discussed gates previously. Like it all kind of fits together, but we actually explicitly discussed the mathematics this week. So I'm sure some of it seemed familiar, but some of it was quite formal. So we're going to try to make it a little bit less formal with this lab. And I want to open it up for questions from last week's content. So you guys can put this in the chat, but as a start, I think it was my other lab section that asked about it, but why we take the complex conjugate when we take the inner product of two vectors. So if we're doing, why am I in red? Let me change my color. Okay, so if we have the inner product of a vector, let's make it a psi, make it look quantum so we also do it like this. We know that this means that we are multiplying the conjugate transpose of this vector times this vector. And a lot of people asked, why do we take the complex conjugate? And again, this dagger is equivalent to a star and a transpose symbol, where this is a conjugate and this is a transpose. And so the reason we do this is that we want our values to, depending on like kind of what's going on, I described it as being always positive last week, and I think it's positive in many cases, but I don't think that's a strictly correct definition. It is always real, and the way you can see this is if you have a psi equal to something that's like I times x, and you want to take the value of the conjugate transpose, or I'll give it another, and I'll do minus I times y. If you take the conjugate transpose, you're going to end up with, when you multiply I dagger or psi dagger times psi, you're going to end up with I times negative I times x minus I times negative I times y times y. And so when you do this, you're always going to end up with a positive number, because a negative I times an I will give you like the I times I square root of is -1. So when you have this extra minus sign, it'll always end up being positive. So we'll end up with x squared minus y squared with this. So that's why you always take the conjugate transpose, is to end up with your signs working out. And I know it's strictly real. I think there's probably some like fun mathematical definition for how you can end up with a non-positive number for it. But I think when you do this, even with two different vectors, you will end up with I think when you're not taking like something like this, which is also taking the magnitude of the vector, I think you can end up with always a real number, even when you're taking the inner product of two different vectors. But I don't quote me on that. But this is the general reason for it. Okay, so I've gotten a question about the block sphere. How is it possible for the first term to be complex in the block sphere? So I assume what you mean is if we have a psi state like this, we normally put our phase coefficient or our phase term on the 1. This is entirely convention. There's not a specific reason for why you have to do it this way. It's all convention. You could have a global phase on the entire thing. That's another phase here. And then you could, if that phase ended up being like negative phi, like if this theta is negative phi, then obviously you've gotten rid of the phase on the 1 state, and you just have a phase in the 0 state. So it's all convention. The way that we draw it on the block sphere, I don't know if you're not necessarily held to this convention, because it all kind of depends where you start and where you end up and what you're referencing to. But yeah, normally we just normalize, or we move any accumulated phase. So any phase difference between the two states, we just place it on the 1 state. Any other questions on this, or on any of the material we covered last week, or I guess to start out your questions about this week? And we will be going through like all the topics that were covered in lecture. So hopefully your question will get answered throughout the course of the lab. Okay, so if there aren't any questions immediately, I will move on. And if you have any questions, just send them on in the chat or raise your hand, whatever you want to do, and I can answer them. So this is this is not lab 5, this is lab 9. But this is the final lab of the semester. It's very sad, but we will be having a little like TA discussion at the end. If you guys have any questions about my lab work, like my background in quantum, like how I got into the field, that will be time for that. And I'll try to leave a reasonable amount of time for that. And we can also go over time if you guys have tons of questions. But then we also are going to be going through vector spaces, eigenvalues, and eigenvectors, which were covered in lab or in lecture, but I was told that it was pretty technical and pretty like formal. So a lot of the proofs that we give, and like I was saying, you can say something that is true in 95% of cases, but isn't strictly true. Like a mathematician would be like, oh, that's wrong. Like that's a wrong statement. But it's true in enough of cases, and like the space of cases that we'll end up dealing with, that it's commonly taught even at like an undergraduate level, and even the graduate level, if you're in more applied math or physics, which is what this mostly is. So we're going to be, I think our eigenvalues and eigenvectors section is like all strictly true, but I would like to note that is something that can be like a bit confusing. We can go through a lot of intense formalism to make the most general statement, but it's not necessarily as intuitive or like particularly useful, especially if you're not dealing with that case. Okay, cool. So as our first example, we're going to be going back to a map like we had last week, where we're going to try to get donuts from home, which we've placed again on just like Highland Avenue, which is up in Somerville, near where I live, but not super close. And we want to go to the donut shop that's right over here. And so obviously there is a straight vector that will take us there, but if you look, there are no roads that go between these 2 points. So what we want to do is we want to take different vectors that will take the roads so we can get to this final destination without walking through people's backyards. So to do this, we can choose a vector that goes along Highland Avenue, and then another one that goes on this little street. I don't know what it is. I see Russell Street on the other side, but the way that roads work in Cambridge, who knows if it's the same road on the other side of the big street. So we can do I guess a vector decomposition. We can decompose it into 2 basis vectors. So we could call this our first basis vector B1, this is B2, and this is a, you can look at them, like we always say, we want to have a orthonormal basis so that we can, or it isn't, I guess the simplest basis is an orthonormal basis, but we want to have basis vectors that cannot be, you cannot compose one of the other, otherwise it's not a useful vector in describing your vector space. And we'll go into a little bit more detail on all of these terms in a second. But we want to choose 2 vectors that are not pointing in the same direction, because otherwise we can't get to our result. If we chose vector, I think I have an example. I'm getting ahead of myself. So if we can instead choose a different basis set, and this is not an orthonormal basis. You can look, this is not a 90-degree angle. This is, I don't know, maybe like 75 degrees. I've just made that up. I have no idea what angle that is, but you can still get to the resulting, like the end location that you want, because they aren't pointing the same direction. But if instead we chose 2 vectors that point along the same direction, even though they're technically 180 degrees rotated from each other, they're still along the same line. And so you cannot get to the Davis squared donuts just adding these vectors up. You can go this way a little bit more, like you could go another length this way, you could go another length this way, but you're never going to end up over here. So there's a lot of different reasons you'd want to choose a specific basis set to work in, and there are different equivalent basis sets that you can use to describe a certain vector space. So we have this now with, we're going to go back to the original vector, and we can add numbers to this and actually describe like how far we're going along each direction. And you can see that we're not in, like these basis vectors are not just a 0, 1 vector, even though they are orthonormal. They are rotated like, I don't know, maybe, I don't know, 40 degrees from a, or 60 degrees from like a normal like XY basis set. So you can have any number of basis sets that could be equivalent within a rotation of each other. So this, although it is, I guess, rotated, you could rotate it back. I don't think I can rotate this whole thing. No, I can't. But you could imagine rotating it like 60 degrees and getting it back to that normal XY setup, so you don't have to deal with all these different rotations. And then similarly, we can add numbers to our non-orthonormal basis set. Or I guess this is not normalized. This is just orthogonal. So I'm sorry for the phrasing confusion, but you can have our non-orthogonal basis set and still get to our resulting location. Although obviously this set is not as efficient as our orthogonal basis set. Our orthogonal basis set, we can go directly up a street and then over. It's a much shorter path. You could have a non-orthogonal basis set that happens to result in a faster path, I guess. If somehow like there was a street that was along this vector maybe choosing a basis set that is like that vector and something like this could be very efficient. But there's a lot of different choices, and they all will give you the same answer if in your like global coordinate system. It's just your relative coordinates will be different. And if anyone's confused, but I think I keep saying global and relative, and they're fairly descriptive words, but if you're not familiar with them, by global, I just mean that we've decided where a certain point in space is, and we've defined that as 0, 0. So I could decide like here is my 0, 0, and I'm calling that's my global reference. And then, but we could also, and so we could define this as being maybe like, I don't know, 2, 3 from our global reference point that we've chosen. But we could also go between these 2 points, and this would be our relative distance between these two, our relative vector between these two. So you can describe things in a lot of equivalent ways, and we're going to be, like all the math that we're going to show is really just more formal ways of doing these same kinds of descriptions. They're nothing magical. If you don't find them intuitive at first, like they aren't anything special, like they're just a convenient way of defining things so that you can do this kind of mathematics really easily. Okay, so now I'm drawing more things. So all of these additions of these different vectors are linear combinations. And what we mean by linear combinations are things that behave like x, not an x squared. So the easiest way to think of that is if you have a vector like this, we'll call this one as x. And I don't want to do that. And we multiply it. Did I do that right? Okay, great. By a matrix A, we are never going to get an x1 squared, like, or an x2 squared out. That's never going to happen. It's impossible for this kind of linear mapping. If you're like for a specific x value, if you chose your x value is 4 and your A matrix happens to multiply 4 times 4, like that's great, but this is a variable, so there's no general solution that will give you an x squared out when you put an x in and multiply it by a matrix. These matrices are always linear mappings, and so they will always result in you getting a linear value out. And you can think of it the exact same way as you see polynomials, which I'm sure you've covered in high school. It's always going to be these linear terms that just behave as x. And so to put this, I guess, in to make it consistent with the notation above, this would be like y1, y2, and it's never going to be equal to this x1 squared, x2 squared term. Okay. Any questions on the concept of linearity? Because it is a really important thing to kind of restrict your thinking for all the math we're doing. And if you don't kind of place yourself in this linear regime, then it can be a lot more confusing. And then I've gotten a question about if eigenvectors always need one of their components to be 1. No. There's no specific reason why one component would need to be 1 for an eigenvector. You might often end up with one of the components being 1. If it's normalized, then you're like if you're working with normalized vectors, then the resulting value will be, or the resulting magnitude will be 1, but that's not necessarily like the actual vector itself does not have to have a 1 component in it. And this equation is x a vector or a scalar. So this is a, I guess it could be a vector or a scalar. I guess a scalar is just a one-dimensional, like a one-dimensional by one-dimensional vector. But yeah, I guess this equation it could hold for a vector or a scalar. But well, for this, like this is not well defined, I guess, for vectors. Like what is the square of a vector? Like you can do like an element-wise square, for it. But I guess for vectors themselves, squares are decently well defined. When you get to matrices, there's like all kinds of weird ways that you have to, you can either take the square of a matrix by like multiplying it by itself, and that gives you a very different value from if you just square each element of the matrix. So in the only case this is really straightforward is if you have a diagonal matrix, which we'll discuss a little bit. And eigenvectors do not have to be normalized, but in general, we tend to work with normalized vectors. But unless your matrix is normalized, your vector does not have to be normalized either. And the thing is with a lot of quantum, our matrices do tend to be like unitary and normalized. So you don't have to have, like, you don't have to think about non-normalized things. And this square, so yeah, like if you did a square of a vector x, and I'm going to note that it's a vector with this little like arrow on top, you could take that to be like your, why did I write it like that? I guess you got your x vector transpose times your x, like that is a fair way of defining a square. But it's not, this is not what you're going to end up with a vector ever. Like you'd always need to have, or with a matrix ever, you're always going to have this variable involved. And this is a very good question, Ben, because we have mostly dealt with 2x2 matrices, and that's because we've only mostly dealt with single qubit gates so far. And with all of our qubits, we just treat them as having the option of 0 or 1. And so everything we deal with is just two-dimensional, but you can have four-dimensional or five-dimensional or n-dimensional matrices. Oh, I guess if you mean like from like having like a column and a row is often described as, or is normally what we mean when we say a matrix. In higher dimensions, you do typically call it a tensor, but it's all kind of semantic. But we're only going to be dealing with two-dimensional matrices, where like I guess our vectors are of, it's hard to describe like what a dimension is because there's multiple layers of dimensions, I guess. So you can have like with your matrices, you have, or I guess if you had a matrix that described a place in like 3D space, you'd have an X, a Y, and a Z. So you wouldn't just have a row and a column, you'd have a row and a column and a third thing. And a lot of times you would call this a tensor, not a matrix, but it's all neither here nor there for the most part. Okay, so now we're going to go to superpositions, which we discussed before, the idea of having a combination of two different basis states with some probability or some probability amplitude for each of these quantum states. And these superpositions are just linear combinations of each of these basis states, or these like quantum states that we've decided on. So we can create superposition states, which we've discussed before, this plus state and this minus state, that are equal superpositions of the 0 and 1 state. But they are 90 degrees out of phase with each other. So this is the plus state, this is the minus state. And on the Bloch sphere, it's just the difference between being here versus being here. But these are still equal superpositions, and everything along this this equator is an equal superposition of our two quantum states if we take them to be our 0 and our 1. And that's all we're doing when we create these superpositions. You could also do this by, well, I guess it wouldn't be super informative to like write it as a matrix, but you could, or I guess you could write your two basis states as a matrix and then write this alpha and beta as a vector. So if you took like your matrix to be 0 and 1, and then this to be alpha and beta, and this would be written as, I guess, I always have it backwards, but 0, 1, 1, 0, alpha, beta. So that's an equivalent, like, you know that if you have any kind of linear combination, you can always represent it as a matrix. Aren't plus and minus 180 degrees from each other? It's minus is e to the I pi -1. So that's, yeah, it's 180. Yes. There. Yeah, no, you're right. You're right. This on the block sphere, this should be 180. You're right. It's always very confusing because we do multiply all of our angles by 2 or by half on the block sphere. So it's always a bit hard to like get things straightened out. But yes, it should be 180 degrees apart, I think. Yeah, because you'll just have a factor of I on your terms if you're 90 degrees. Yeah. Yeah. So I'm very easily confused with the factors of 2. It does make visualizing it a lot easier, but it is very easy to get confused on it. So yeah, if you're ever confused about a factor of 2, just like, you can just randomly multiply or divide by 1 and hopefully it'll turn out right. Because there's just factors of 2 that appear everywhere that I can never keep track of. Yeah, cool. So, oh no, I've drawn over important things. Why do I always draw over things? Okay, so we have this state. I can just erase this, I guess. Okay, so we can make a linear combination of these other basis states as well, and these are also an orthonormal basis. You can see that they're normalized by our factor of square root 2, and they are like orthogonal to each other. But yeah, cool. So yeah, I think that's all I have to say on this. Are there any questions on superposition? I think it's really straightforward to think about it just as this linear combination. There's nothing magical about the concept of superposition. I guess it's just you don't expect to be able to have a combination of 2 discrete states. But the whole thing with quantum states is that the reason we describe them as superpositions of these states is that they are these two, like it is in fact these 2 discrete states. It's not equivalent to just like go straight out without describing it as a superposition, but the 2 states are interfering in some sense. And that's the whole thing with quantum mechanics in general, is that you have interference between your different states. And that is like the #1 most important thing. Do I have my 1 and 0 state backwards? It might. If it's backwards, I can fix it. Yeah, no, I agree. This should be, yeah, this should be the other way around. Again, I just don't have any ability to do things, to remember anything. So I have to just derive everything, and everything that is convention, I will forget and do backwards. But the convenient thing is if you do everything backwards, you'll still get the same answer. it's completely fine to just treat your 0 state as your 1 state and your 1 state as your 0 state, and then flip them at the end if you're like, oh, I should have gotten the other thing. All the math will still work out. So cool. Yeah. Now we can write a state as a linear combination of these two states. And I guess I had let you guys write it out, but it's pretty straightforward. We can write it as a vector, and we can treat our 0 and 1 as being in the x and y direction. So this is our 0 here, this is our 1 here, and again, this is 90 degrees different, or like it's a factor of, not 90 degrees, it's a factor of 2 different than on our block sphere representation. You can see these are 90 degrees apart rather than 180 degrees apart, while they're 180 degrees apart in our block sphere. So everything you just have to multiply all your angles by a factor of 2 to go to the block sphere representation. Yeah, so to represent these, oh, I guess we just kind of jump right ahead, because I mean it's kind of clear. You just have 3/5 1 0 plus whoop, I wrote that in the wrong order, plus, well, -4/5 0 1, and then we've just changed it into or we've described it in this basis, or this linear combination of these two states. We can do the same thing with our plus and minus basis. So our plus and minus basis is on the diagonals in this 2D representation. And again, we do have this factor of 2 difference. They're 90 degrees different in a 2D representation and 180 degrees different in the 3D representation on the block sphere. But you can see this is just along the 45 here, but these two states are still 90 degrees apart. And we can do a similar like decomposition into these two states. Yes, would anyone like to try their hand at mathematically giving how many, how much of a, or how big of a multiplying factor you want on each of these states? It's probably not that hard. I can't imagine doing math right now, but I can work through it if people are interested in seeing how you'd get to it as well. I'll start working through it. And if anyone else gets the answer before I do, or gets a correct answer while I manage to do it incorrectly, then we can, I guess there's definitely, you want to, the idea with these two states is we can adjust the relative value of our, I guess, like second element by the fact that these are, like, this is negative, this is the negative of our plus state. And similarly with this, we can just adjust the relative values and then scale the whole thing. Yeah, so let me see if I can figure out how to do it. We have not been given, oh wait, no, we have been given, no, we have not been given that. I thought I'd written, I was like, oh, maybe I wrote it down earlier, because I went through it at one point, but I don't remember the value that I got. Yeah, so we can just, we know that we want the top state to end up with us getting 3/5. So we have our 1/√2 times alpha plus 1/√2 times beta equals 3/5, and our 1/√2 times alpha, minus 1/√2 times beta is equal to -4/5. And so you can add these together, and this gives us, so if we add these two, we can get 2/√2 alpha is equal to -1/5. Therefore, alpha is equal to 1/√2 times 5. I'll write that in this. Why did I go to the next slide? Yeah, let me write that in a less ugly form. 1/5√2 negative. And then you can back solve for the other value, or you can instead subtract the 2 to get our beta value. So I guess, I don't know what's the cleanest way to do it, but if we know that 1/√2 times alpha plus 4/5 is equal to 1/√2 times beta. This is just rearranging the second equation. And then that gives us -1/10 plus 4/5 is equal to 1/√2 beta. Okay. And that is 8/7 times √2. Great. I've managed to do math. I'm so proud of myself. Shouldn't it be multiplied by square root of 2? It should be multiplied by square root of 2/2, which is equal to 1/√2. So it's either way. This is the same thing as square root of 2/10. Because you could just multiply both sides by √2 and 2. So it all works out in theory, and in reality, I think I have done it correctly. I'll double check it before I upload it to Canvas. But yeah, that's how you do this kind of decomposition into a linear combination. Yeah, I guess the tricky thing is a lot of times we work with only rational numbers or whatever, where we have our square root of 2, or we only have rational numbers in our denominator. So we have our square root of 2 on top and then 2 on the bottom, but it's all equivalent. So this is a very good question, Amo. If we have 2 vectors that are parallel, can they be in a linear combination together? Well, why want to go to the next slide? Yeah. Just any 2 vectors. Well, we want to try to write this state as a combination of these 2 vectors. I'm one of you guys. I'd like you to write this out for me. How would you do the decomposition? I mean, you saw how long it took me to do the decomposition. So don't try too hard, but think about it for a second, and tell me how you would do it. No answers? Well, this was a trick question because they're in the same direction. And you can see this if you plot it out. Even though this is negative, it's just, you could write this instead as -2 over square root 8, 1, 1. And then it's in the same direction. It's not actually equal. But the other one is just 1/√2, 1, 1. So this is just a factor of, I guess, it's actually no, it's exactly the same. They're different magnitudes, or they can be different magnitudes, but these are actually the same magnitude as well, which is even more this is a specific example that is actually totally accurate more generally. It doesn't have to be this. You could have instead this could instead be 4/√8, and this would still you still could not create this state with these 2 vectors, because these 2 vectors all point like this. like the magnitude of one is maybe twice the other. So with the new version I wrote out, where one is twice the magnitude of the other, they still point in the same direction. So you can't create any states that aren't along this line in space. You could not create this vector, you couldn't create this vector, you couldn't create this, you can't create any of them. You can only create vectors that are along that line. And that's what's really tricky about the blocks here, because we do have our two basis states like are shown pointing in opposite directions. But that's actually like not like, it's because we've multiplied all the angles by a factor of 2 to make it easier to represent. But if they were actually pointing in opposite directions, we couldn't describe any states with that. So it's all very confusing, and I think I like the block sphere a lot. I think it's very intuitive, but it's very easy to get confused when you start trying to do math with it. I think it's a pretty poor mathematical tool, and that's why mathematicians use a different block sphere that's actually like got the correct angles on it. Yeah, cool. So now linearly independent vectors are vectors that cannot be written as combinations of each other. So our 1, 0 state and our 0, 1 state, you could not multiply this vector by anything to get this vector. Like these are not equivalent. Like you could multiply this by alpha, this by a beta. There's no way that you can get a 1 to appear in the second element, or a 0 to appear in the first element if you're just multiplying it by a value. I guess, yeah, if you multiply by 0, that's the trivial solution for everything, is you can just multiply by 0. But then even if you multiply by 0, then you just have 0, 0, and you still don't have the 1 in the bottom to go between the two. But yeah, then in theory, you can cheat a little bit by multiplying things by 0. And there are a lot of things that you can solve by just multiplying by 0, but that's always called like the trivial solution, because you just multiplied by 0 and you moved on with your life. But it's normally not a useful or a physical solution for most problems. Although it is kind of satisfying to just give that solution and then move on. Okay. We also have the concept of a span, which is all the vectors that can be written as combinations as the given vector set. So like I showed before, like the span of 2 linearly dependent vectors is just that line in space. But if we have these 2 linearly independent vectors, we can describe everything in 2D space with those 2 vectors. But again, we do only have, these are 2-dimensional vectors. So you can only describe 2D space with them, or you could describe a plane in 3D space if you wanted, but they're not like sufficiently useful in 3D space. You need a third element to describe things in higher dimensions, or like a fourth or fifth, or your n-dimensional space. So all these terms also apply to higher dimensional objects. We'll only be dealing with 2-dimensional and sometimes 4, or I guess like, yeah, 2-dimensional and occasionally 4-dimensional spaces, where we still mean like these are 2D matrices, but the length of, or like the number of elements in the columns or rows is that dimensionality. So these are just some examples of vector spaces. A vector space is just a descriptor, again, of all the vectors that you have available to you, all the vectors that you're interested in dealing with. You can choose a specific vector space that you're interested in. So this is a 2-dimensional vector space. There's also all the vectors on the surface of the block sphere. So like all the normal vectors to the block sphere. And that would be, I guess, 3-dimensional. I guess it's a 2-dimensional surface in a 3-dimensional space. So there's a lot of subspaces within larger vector spaces. So you have like a vector space could be all 3-dimensional space, but then a subspace could be a 2-dimensional region, like a 2-dimensional surface within that 3-dimensional space. So it can be a 3-dimensional, I guess a 2-dimensional surface that moves within 3D. So if you had like with this, this surface does move within 3D, but it is a 2-dimensional object still. And so there's a lot of different dimensionality that you can do with. We're not going to be dealing with too much of this like kind of more advanced, confusing like geometry, but it is, I guess, interesting to note. And then we also want to, like, I guess I've described these as basis vectors for quite some time. And we've discussed the concept of a basis vector for a while. But the vectors that you choose to describe all of the vectors in your vector space are your basis vectors. And there are equivalent basis vectors that you can use. So here's one that we showed earlier. We also have our plus and minus basis state, and there is an infinite number of basis choices for any given vector space because you can have any like finite rotation of these two vectors. Like they're always going to be 90 degrees relative to each other, but your global phase of the two can be rotated slightly. So what we've done with these two vectors, I guess, is we have, I guess, rotated them 90 degrees on the block sphere or 45 degrees in 2D space, which you can see by like our original vectors were here and here, and we've just rotated them 45 degrees down. And that's all you do. Yeah, so here. That's all you do to create other basis vectors in a 2D space. And you can do a similar thing in 3D space and in infinite dimensional space. It's all just this rotation. It's just really hard to visualize when you get to higher dimensions, but computers are really, really good at doing it because it's just multiplying your vectors by a rotation matrix that will rotate it in whatever space you want by whatever angle you want. So that's really nice that you can very easily go between different bases just by rotating. So any questions what we've gone through so far? I've taken way longer on, I guess, the basics, but I think if you like really are like, I get vectors, and then you go to eigenvectors and eigenvalues, then it's like, oh, this makes perfect sense. But if you're like, then you go to eigenvectors and eigenvalues and it's confusing. Okay. So I will try to push ahead, but if you guys post any questions, if you think of one, like just post it and I will get to it eventually. But I'll try to push ahead just for the sake of time since I don't want to hold you guys over time. So question of why we might want to use different bases. Well, we have our example from earlier where it's much more efficient to go this basis route versus this basis route. But there are other reasons that you might want to do that. So when we're going to go to give this example, I'm going to go back to the gates that we covered last week, where we have a C gate, and we want to multiply our input vector by our Z gate to get our output vector. And so we could choose, we can choose, or we can have like a random vector like this 3/5, -4/5. Multiply by this, and we can crank through, just multiply each term and get the result. But we could also use a basis vector for the Z gate, and when we can use our original basis vectors when multiplying by the C gate, and you can see that when we do that, we get, if we put in the 0 state, we get out. Or we didn't actually go, I don't actually have the result yet here, but we multiply this by this, or we multiply our 0 state by our Z gate, and we just end up with the same value out times 1, which is our, I guess in this case, this is our eigenvalue and this is our eigenvector. And I'll just go to the written out version so I don't go through things too slowly. I'm sorry I'm like kind of like all over the place. I'm trying to rush just because I always go so over time and I feel bad holding you guys late. But the idea of these eigenvalues and eigenvectors is when you have an eigenvalue of a particular matrix. And so eigenvalues and eigenvectors are specific to the matrix. So this has an eigenvalue and eigenvector. And it actually, like, if it's a two-dimensional matrix, it will have two eigenvalues and two eigenvectors. It's the number of dimensions of your matrix. If none of your rows are the same, like none of the rows can be decomposed into a linear combination of other rows in your matrix, it's like the number of unique rows of your matrix. It's a very similar concept to the idea of like linearly independent versus linearly dependent vectors. If two rows of your matrix are linearly dependent, then you don't have a unique eigenvector eigenvalue pair for that row. But otherwise, every row gives you an eigenvalue. Linearly independent row gives an eigenvalue and eigenvector. And when you apply a eigenvector, which like it's often called like a characteristic vector of that matrix, and these eigenvalues and eigenvectors are defined for each matrix. So there is an eigenvalue, or there's two eigenvalues and two eigenvectors for each of our gate matrices. When you apply matrix to, let's say this is our initial state. This is our, I forget what the we normally use like a lambda for eigenvalues. I forget what the symbol is for eigenvectors, but I'll just say like this is our A vector. If we multiply it by our Z matrix, ZA will always be pointing in the same direction. And that's the whole special thing with eigenvalues and eigenvectors, is they just end up scaling your eigenvector. Or if you multiply a eigenvector by its characteristic, or by its matrix, then you'll just scale that eigenvector to be larger by its eigenvalue. So this is its eigenvalue. And so that's all that this operation does. And you can have a negative eigenvalue. That's totally fine. It can be any scalar value. The important thing is that you end up with the same vector out. And so you just end up moving along that line. What's important about this is you can see if you apply a Z gate to your zero state, you'll just stay in the zero state. So they're very like it's like a stable, like characteristic operation. So if you are in the zero state, you won't move anywhere if you apply this this matrix to it. And similarly, if you're in the one state, you won't move anywhere. And that's really important for doing different algorithms. Like if you want to, or if you are operating in the like eigenbasis for your gate, then you'll be less susceptible to noise and like different things with regard to that. This one thing, so these are all like technically you can have more eigenvectors and eigenvalues. You could say, oh, I could also write this as half times like 2, 0 instead. But this is the same vector. These are linearly dependent. So you want to always have, like what we're talking about is always linearly independent vectors, linearly independent values. If you can write a particular vector in any number of ways, but it's not giving you more information if they're still in the same direction. That's really the important thing with all these vectors, is never really the magnitude, just the direction. And how do you know which one of these to use? I mean, you can use any of them and get the right value out. With quantum states, you want everything to be normalized. So you always want to use the normalized version for your vectors. So it really reduces your your options, which is convenient, but it's also convenient to normalize everything and then just work with normalized numbers, because then you don't end up with like random things out. And if you screw up something, you know immediately because your result is no longer 1 when you take the magnitude. So it kind of builds in like a nice little check to make sure that you've done all your math right. Cool. So yeah, these are all pointed out. And if you want to find if a particular vector is an eigenvector of the matrix, you just multiply it by the matrix and see if you can decompose it into an eigenvalue and the same vector again. And if you can, then you know it's an eigenvector, but you'll also quickly like learn the eigenvector eigenvalue pairs for the relevant gates. So if you don't understand it super well and you just want to use what or you just want to like use it as little as possible, you can just memorize the ones that we use for like the X, Y, Z gates. Yeah, so why do we want to use these eigenvectors? So I've given like a bit of justification like physically, but it also makes it much easier to perform the math on these for these gates. So you could multiply through all of these terms, and with these gates, they are pretty simple, pretty straightforward. But if we use our eigenvectors, we can decompose this vector. So let's like ignore this bit down here at first. Just look here. We're decomposing this into these two eigenvectors. And when we do that, we immediately know the results of the Z gate times these eigenvectors, because we know they're eigenvectors of the matrix. We know that this will just give us a 1 times it, and this will just give us a -1. And you can, with this simple of a matrix, because it is, I guess, just like you can see pretty much the same result without decomposing it. It's a good example, but maybe doesn't make clear how useful it is immediately. But if you're working in the plus minus basis, maybe it's not super clear. You have to multiply every single term to get through it. But if you just decompose it into these two, into its eigenvectors, then you know what's going to happen to each term. So this is a good reason to use these eigenvectors. So we have this example that if you don't follow it, I won't judge you. I didn't get it at first either, but I think it is kind of useful. If we have a car, we know how each component of the car works. So we know how a particular wheel works. Maybe we know that it has some diameter. So if you're moving at some speed, you're going to roll around the wheel like a certain number of times. We understand like this small system of the car pretty well. We can similarly describe the body of the car with like the length, the width, the height, like the area inside of it, the curvature of the edge. And we can describe the engine with like the horsepower of the engine. When we want to describe a car, we could say like, oh, okay, we have 4 of this particular wheel times 1 of the body times 1 of the engine. And you can use these same component parts for different cars. So now we have the same body and the same engine, but we want to have 6 wheels instead. But because we know how each component part works, we can guess how, or like we can not guess, because we can calculate how this now larger, more wheelful car will work. And that's the same idea that we use for eigenvectors. Is we know how to work with these specific eigenvectors. We know what we get out putting this eigenvector in. We get a certain we get a certain eigenvalue out when we perform a gate on its eigenvector. So we can combine these eigenvectors to create different qubit states. And so if we're applying a Z gate onto a certain state, and we know that there's some component of that state that is an eigenvector of the state, we know it's not going to move that. It's not going to move that component of the state. But if there's another component of the state that is not an eigenvector of that matrix, then it will move that portion. So it's a convenient way for working with these matrices. Okay, so this is, I know we're like right at 8, and I'm just going to quickly go through this example, and I can go through it a little bit more slowly if you guys want to, and then I guess we'll just go over time if you guys have any questions about the field or anything. Yeah, so here's the eigenvectors for the x gate. Instead, they are the plus minus basis instead. So if you multiply, this is our plus state, this is our minus state. You can similarly see that these we'll get these eigenvalues out where this is 1, this is -1. So we've just, I guess, rotated it 180 degrees, dependent on which state you put in. But this rotation on the block sphere is just staying in the same spot. So you don't see it at all. Technically, there is, I guess, a phase on the state, but it's not the same, like it's not a type of phase that will cause it to interact with other states differently, although it can accumulate when you perform more operations. Yeah, so these are the eigenvectors for the x gate. And so if you want to use these eigenvectors, and this is, I guess, the more complex example where you really see why these become useful. If we have this state and we want to multiply it by an x gate, we can decompose it into its 2 constituent parts. This is our minus state, this is our plus state. And then we can perform the x gate on each of these eigenvectors by themselves. And we just get out the eigenvalues for each of these eigenvector states. And we'll get the resulting value out. And what's, I guess, convenient, I guess it's I don't even know if this actually is that much easier mathematically, but it allows you to, I guess, decompose a given state into states that you might care more about, like these superposition states. Maybe we care more about getting the information out of them. And so we want to know exactly what happens to those states, while maybe we don't care about like the total combined state. So this is a more like physical interpretation than just taking this arbitrary vector and multiplying it through this matrix. So yeah, I guess doing this decomposition into these 2 basis states, these 2 eigenvectors, is not that straightforward. It's a little bit more complicated than just doing this multiplication. But once you have the eigenvectors for your system, it's really easy to perform the mathematics to get the resulting value, because you know the eigenvalues for each of these states given you multiply it by this X matrix. Yeah. So just to review, since we're a little over time already, a vector space is just a collection of vectors. And a given qubit state can be expressed as a combination of 2 or more states in this space. If you are in a 2-dimensional space, though, you only need 2 2-dimensional vectors to describe everything in the space. And I guess you need more for higher dimensional states. And like your normality condition is different. Like there's 3 normal vectors in 3D space. So if you have 2 vectors that are normal to each other, or sorry, not normal. So if they have 2 vectors that are like orthogonal to each other, then you can describe any vector in a 2-dimensional space. But you can also have more vectors, more basis vectors, if you want to have a non-orthogonal basis. Just, you can always decompose that non-orthogonal basis into an orthogonal basis. You will never need more than two vectors. And that's the concept of linear independence. If you are using more than 2 states, or more than 2 vectors, the third vector, or you will always be able to create a third vector from the 2 other vectors, if you can access the entire space with those 3 vectors. There will always be some redundancy between them, even if you don't see it immediately. Like it will always be there. And then there's the basis that we choose for a specific vector space is like what we call this, these states that we're using to describe the vector space. Applying a gate to its eigenvector will always result in the same vector times a constant. This is we're describing this as in terms of a gate. This is specific to any matrix. Any matrix will have a eigenvector and eigenvalue. And then applying a gate to any other vector could be broken down into 2 steps, where you convert it into its eigenvectors, and then you apply the gate to the eigenvectors, and you know that you'll just get the eigenvalue times the eigenvector. So that was a lot of words. Why do we care about all of this? Well, we actually do use all of this math all the time when we're describing a quantum computer, when we're trying to control what a quantum computer is doing. So if we want to apply a X gate or a Y gate or a Z gate, we apply some microwaves that are a certain time duration to cause this rotation around the Bloch sphere and to perform this gate on the qubits. And the reason we use all these vectors is that we, if we want to, if we want to describe it as like a magnetic field or a spin, which is a common way we will call it, we don't just have a value for the spin, we have a vector. So a lot of times we'll describe it as a spin up or a spin down. And these matrices all apply to physically what's happening with all the words that we use, I guess, are kind of based off of how atoms are treated, or like, I guess originally the examples were electrons and then like, I guess, ions. So like atoms that have some spin or like some, I guess originally they were charged atoms just because that was easier to work with, but they do have neutral atoms now that behave this way. And all of these systems do behave in the exact same way as all the math that we've covered. So yeah, that's why we care about this. It is all exactly mappable to what you do in lab. But yeah, any questions on this? And also, yeah, if you have any questions on, like, we're past time, so if you guys have to go, thank you so much for the great semester. We're gonna start up again, I guess, in like 3 weeks-ish. So if you're staying in my section, I'll see you again. But also, if you have any questions about my like lab research, I can try to answer them quickly. I don't want to hold my moderator too long, but I can try to answer some quick ones about how I got into the field or what I do in lab. But yeah. Okay. Thank you. Thank you, everyone. Yeah, let me, I can also kind of give like a little descriptor of what I do if you guys are interested. Actually what we showed on this previous slide, this is a solution refrigerator with a superconducting chip in it, and that's actually what I work on. I do specifically quantum simulation with superconducting like quantum computers. So what you do is you have a specific like system that you want to pretend to be. And so with any quantum system, you describe it with your Hamiltonian. So like the Schrodinger equation here, this is your Hamiltonian. And what we do is we try to create a specific Hamiltonian on our quantum computer, and then it acts similarly to something that we care about. Like maybe we care about like some material that has a certain Hamiltonian, and we can examine the dynamics of that certain material using using its same Hamiltonian, but in a controlled quantum system. So it's a pretty cool thing to do. Oh, so I've gotten some questions while I was rambling. Yeah, if any recommendations for high schoolers getting involved in quantum? I mean, I guess this is a great start. I didn't really know anything in high school. I knew I was interested in physics, but actually in like middle school, I really wanted to do like theoretical physics, like astrophysics. Like, I thought that was super cool. And but then I was like, oh, I should do something practical with college. And so I was like, I'll major in mechanical engineering. And I had no clue. Like, I knew what mechanical engineering was because I figured you built things, but then I ended up switching to electrical engineering like a month before classes started because I found out that electrical engineering was not changing light bulbs. And I didn't know that until like literally like a month beforehand, and maybe 3 months beforehand. But then I like finally got around to changing majors like a month beforehand. But yeah, like I've been doing anything is really, really, really the best thing you can do. Like just like taking courses like this, reading, like there's like some nice intro textbooks. I think I've referenced it a few times, but there's like Isaac Chuang and Michael Quantum something textbook is really good as like an intro. Also just like Qiskit and Qtip, the softwares are both Python packages. Qtip, Qiskit. These are free. They're in Python. You can mess around with them. We're going to be learning Qiskit next semester of the course, but like they're totally free to work with. And that's like, I think if you actually want to kind of get more involved in like quantum research, you can't do experiments. Like what I do is like definitely infeasible for like being in high school unless you somehow got involved in a lab that has access to all this hardware. But the software stuff is just like super accessible and completely free. So that's like I guess some easy ways to get involved with things. I think just like learning as much as you can is helpful. And if you really want to, there are depending on like where you live, there a lot of times like well, infrequently, professors will take high school students. For some reason, there are certain programs that get high school students involved in like research. I know there's one called there's like an REU, which is research experience for undergraduates. That's through NSF, and I believe the NSF, like the National Science Foundation, if you're in the US, has a program like that for high school students. And so that's like a cool thing you can do. But it's not like, it is like a little bit inaccessible. Or if you live like near a big national lab, like you live like near a NASA location, like you can work for NASA for a summer. But like all those programs, like they don't accept many people, and normally like they primarily exist for people that they already know, and they just somehow got funding to like let people they already know go and like do stuff in labs. So it's like people act like it's so accessible to like get involved with that in high school, but it's actually like you have to know people a lot of times. So I wouldn't feel bad if you like can't get something like that. I think doing theory like this is at least as useful. Got any question if it's expensive to buy a superconducting material? Yeah, all of this equipment is really expensive. Like a dilution refrigerator is like $1 million. And then to cool down a dilution refrigerator, you use a combination of helium-3 and helium-4. And the helium-4 is like really expensive, or I think I have that right? I might have it backwards. But it's really expensive, and it's like restricted by the US government. Actually, you can't buy it. You have to get a contract from the US government because it's actually like nuclear waste, and there's a finite supply of it on planet Earth. And so it's really hard to like get your hands on it. It's like pretty much invaluable. And these dilution refrigerators cycle all this material so you don't run out of it. But it is like very, very important and expensive. But the superconducting material you use in it is not as expensive. We actually use aluminum, which is only superconducting below like 1 Kelvin, which so we don't care because we're in a dilution refrigerator where we operate at like tens of millikelvin. But if you want like a high temperature superconductor, then that's like more expensive, I think. But you can also make your own if you like have like a chemistry lab, I guess. And so yeah, there's I also got a question about my favorite project I've done so far and why. I guess like research projects are all very big scale and like long term. So the project, so I switched research groups partway through my PhD, which is not super common to do, because I just like didn't really like the work I was doing previously. And so I previously worked on nitrogen vacancy centers in Diamond, which are also like a type of like quantum system, like they're a 2-level like quantum system, but you instead work with the like spin states of this defect that exists in diamonds. The whole idea is like a diamond is made of carbon lattices. I was going to try to draw it, but I'm going to mess it up. But you have just like a substitutional nitrogen atom instead of the carbon that's normally made out of. And that can have a certain spin, and you can address the spin with light. And what's really fun is if you have access to a diamond somehow, you can shoot a green laser pointer at it, and it will glow red, but you won't be able to see the red because there's so much green. And it will also like shoot the light everywhere. So don't do this actually, because you'll blind yourself unless you have laser safety goggles, which aren't actually very expensive. They're like 20 bucks, and they're like, for a green laser, they're like orange tinted goggles. And you can just buy a pair of that and then shoot a laser pointer at a diamond. If for some reason you have access to a diamond, like if you have a parent or a family friend that has a diamond ring, just like shoot a laser point at it and you'll see it glows red. If you have these goggles that will filter out the green light. So that's what I used to work on, and it's like a pretty cool thing, but I didn't like it as much. And now I like this quantum simulation stuff. And what I'm really interested in doing is trying to look at like interesting, like kind of like magnetic systems. I think that's like the magnets like are just the coolest materials, and they're not really well studied because they're kind of like irritating materials. They're like to fabricate, like not to like, the theory is also like honestly a lot, there's not a like there's a lot of magnetic theory, but a lot of it is still unknown, surprisingly. And I think that is like a really cool area. And it's not just like magnetic like the classic like ferromagnet where there's like a permanent like magnetic moment, or like I guess a lot of things have a permanent magnetic moment, but like where you permanently will attract things to your magnet. There's different like types of magnetic materials, like anti-ferromagnets, where there's actually net no charge because all the spins are pointing in like opposite directions adjacently. And so like we didn't even know this existed until like more recently, until we could scan a material and see that the spins are pointing in different directions. So yeah, it's super, there's so much super fun stuff that you can do like in lab. Like honestly, highly recommend just doing a PhD so you can convince the government to give, I guess, your PI a lot of money to buy stuff, and then you can just like have fun with it. I mean, we do produce like useful things. Like I am like, I've done a lot of like unpleasant grunt work trying to scale up our qubit chips. So we have like many qubit chips, and that will inform like future designs of quantum computers. So, like it is productive, but it's also just like fun, and we get to like poke around with stuff in lab and like try to simulate like interesting things. Like it's there's a lot of like fun stuff you can do. Also gotten a question if you think that pursuing the field as a career is risky when it comes to finding jobs. No, not at all. Because, so the thing is, what's fun about doing a PhD in a STEM field, and it is maybe less easy depending on where you go for your PhD, but you can very easily just bail into finance or software, and anyone will hire you with a PhD in like quantum. Like no one will be like, oh, like I don't know if I want like a quantum engineer as my like financial analyst. Like people will hire you to do nothing even. Like I've gotten like I've had friends who have gotten offers from like startups that are like, yeah, we don't actually need you to do anything. We just want to say that we have like an MIT quantum engineer on staff. They're like, no, I'm not going to do nothing. It's so like there's a lot of it's very easy to like go into business or finance or computer science after doing a PhD in physics, and a lot of people like or math actually, and a lot of people do. But yeah, it's pretty funny how easy it is to get jobs. And I get like emails from like all the big like consulting firms like a couple times a month being like, hey, would you like to like come to our info session and like get a like work for us? And no, not really. I'm doing a PhD, and I will be doing a PhD for another few years. But it is really nice that there's not that much risk, honestly. Like you don't make very much money doing a PhD. So that is like a concern if you have student loans or you need to help out your family. But like you make enough, especially if you're at like a big university. Like some smaller universities don't have as much funding. But yeah, there's a lot of it's surprisingly easy to get a job with the field. And there's also like a decent number of jobs in quantum now that aren't in academia, like at IBM and Google and Microsoft. You can do all kinds of stuff. And yeah, what the different aspects of quantum science other than quantum computing? I mean, technically like all physics that people do now is like quantum pretty much. Like I guess like astrophysics doesn't really deal with any quantum things, but like any condensed matter physics, which is like the physics of solids, like semiconductors, like what's in your phone, or like superconductors, like what's a superconductor. That all is done using quantum theory, but it's less like direct quantum theory like what we do, like in this course. But it's still like quantum science. And there's also like atomic physics where people like freeze atoms in place using lasers. So they do this thing where they like focus a laser down to a very skinny little point and they trap an atom there. And then they like shoot microwaves at the atom and control its spin that way. And it's really cool. So there's a lot of different areas of physics that like are all kind of quantum conforming. This all behaves exactly the same way as all the quantum computing we've been talking about. And in a large part, like a lot of the physics, like a lot of the pure physics that happens is technically quantum computing, or like is directly applicable to quantum computing. Like you could use it for quantum computing. And they do tell people, like they tell like funding agencies like, yeah, this is useful for quantum computing, but that's not really what people are interested in. But it is totally true that learning more about how these systems work is exactly like applicable to quantum. So, yeah. Also gotten a question if there's any internship opportunities in the field of quantum computing that you recommend. I mean, I guess the big players in quantum computing are IBM, Google, and Microsoft. Those like the three like big companies. There's also some smaller companies like Zapata, and I don't know if Rigetti is now defunct, and D-Wave, which is also like they're not defunct, but like some of like a lot of them aren't really hiring because they're like small companies like startups. Those are like the companies I recommend looking into, but it's honestly like there's a lot more opportunities, especially as an undergrad, to just do research at a university for the summer. And there's programs like this NSF REU program that will pay you to do the research. So if you're at like an undergraduate level, you can easily do something like that. But yeah, okay, so we are getting close to 8:30. So I have to go, but if you have, I guess, any more questions like about like the field or like advice, I can definitely answer them on PUAT. So like that's a totally fair question to ask. It doesn't all have to be technical questions because this is this course is meant to be kind of an introduction to the field, not just an introduction to like the science aspects. Yeah, thank you all so much for staying over time. I hope that I answered enough of your questions. But yeah, and I'll see you all in 3 weeks, assuming that you all stay in the section. Yeah, thanks everyone. And I'm gonna stop my share. Yeah, I hope you all have a good break and have some time to like rest, relax before getting right back into quantum next semester. Okay, bye everyone.